Hello everyone, today we're going to solve daily LeetCode problem number 416, partition equals subset sum. So in this problem we're given an integer array nums and we should return true if you can partition the array into two subsets such that the sum of the elements in both subsets is equal or false otherwise. So we have a few examples where we provided with nums 1, 5, 11, 5, and we can see that we can add 5 to 5 and add that 1, it will be equal to 11. That means that we return true. And if we have 1, 2, 3, 5, false, because we cannot make it in equal parts. So better look on this problem from the story perspective, like the treasure division dilemma. So imagine a group of adventurers who have just found a treasure chest, nums, filled with gold coins, our numbers. So each coin has a unique value, like 1, 5, 11, 5, or 1, 2, 3, 5. And the adventurer want to divide the treasure equally between two groups, but they're not sure if it's even possible. So it can be true or false. So the problem, can they split the gold coins into two piles with the same total value? We can use dynamic programming subset problems to resolve this. So the efficient magical ledger. So to solve this dilemma, they use a magical ledger, but with clever twist. The ledger helps them keep track of all possible sums they can make with the gold coins they have seen so far, but it uses less space. So first, we have the target. So we calculate the total value of all gold coins. And we can make this using sum function. And start coins will equal sum of nums. Then we will check if total value is odd or even, because we understand if the numbers are not divisible by 2, so there is odd, then immediately it's possible to divide the treasure equally and return false. So we will save our time. So if coins and on, so it's impossible to divide it, it's odd, we immediately return false, saving our time. So for example, if inside of our array will be 11 and 2 5s, totally 21, it would be impossible to divide them into groups. Now we need to calculate the equal share, something that each group of adventure would get. An equal share will be our coins divided by 2. So 2 halves. Next step, we compact a ledger. Instead of grid, they use a single row in the ledger. The indices of this row represent positive sums from 0 up to 12th value. Initially, they set the first cell index to 0 as yes, because they can always make a sum of 0. So we will make dp, our dynamic programming function, it will be false. We multiply it by equal share plus 1, and initial first row will be equal true. Then we start adding coins, so updating ledger from both sides. 1 by 1, so for this we will use 4 coin in nums in our treasure box. So for each coin, they traverse the ledger backward from the target sum, our equal share, down to the coin value. This backward process is crucial to avoid reusing the same kind in the single sum. So we start a new for s in range where we have equal share, we have coin -1, and we have -1. Then we will use dp of s, and this will be equal to dps or dps minus coin. So for each sum, they check if they can reach it. Either they could already reach it immediately, dps and yes, or they can reach s minus coin, means yes and the current coin to it. If either of these conditions is true, they mark our dps as yes. And the lastly is treasure fate, and our fate is to return dps of equal share. So after they consider all the gold coin, they look at the last cell of the ledger, index equals share. If the cell is yes, true, it means they can make that target sum using the gold coins, and therefore they can divide the treasure equally. If it's not false, it means they can divide the treasure equally. So let's run our code, and it's acceptable. Let's submit. And it's pretty efficient. In memory use, very efficient. So how will you use dynamic programming here to resolve this specific problem with splitting coins in equal shares between two adventure groups? We use the single row ledger dynamic programming efficiently store the result of subproblems, whether a specific sum can be made with subset of coins. Then we build solution iteratively, updating the ledger using previously computed result. Then we backward traverse ensure that each coin is used at most once in treasury sum. So this optimized approach reduces space complexity, quite optimized for memory use, while maintaining the correctness of dynamic programming solution. So while we split it in subproblems, which help them understand that to resolve problem, we should really understand what is required and have the model, because most of problems are already proven with, already resolved with some type of method. So instead of creating our own method of resolution, we can go to already provided methods and combine them for our specific problem, creating even greater solution. So thank you for your attention. If you have any ideas or comments, feel free to leave them down below, and have a nice day. Bye.